class, what is the last point here? This is 10 to the power 3, right? Okay, 10 to the power 3 times sub-30 times your bandwidth here will be equal to 10 to the power 6. So what do you get? Your T divided by your K will give you your bandwidth, which is in this case will be equal to 10 to the power 6 divided by 10 to the power 3 equal to 10 to the power 3. That will give you 10 to the power 3. So that is basically how a 60 dB will look like. Okay, the one who asked for probe, are you asking for this question? Who is the guy? Who dropped me the email? Yeah, I'm going to answer this question anymore. Okay, whoever asked me this question, I answered the question today. Now, what is the next question?
What's the next question?
Trigger is the positive effect.
Why it's coming up right here?
What are applications for triggers? Right? Okay, what's your next question? Idea of meter is 2 semesters ago, right? Okay, last time or I can't remember. Okay, the next question. So how's the idea? Okay. This one, idea meter, I showed it during the last lecture. Okay? Often I didn't bring my circuit for you to see. Alright? The very last one. The last lecture I mentioned it before. Somebody will have taken it or whatever. But it is far too complicated. Okay? But as far as voltmeter is concerned, it's much easier. Now, voltmeter typically. Now, in terms of concept, our class, ideal ammeter. What you need is 0 ohm. Okay. Ideal voltmeter, infinity ohm, equal impedance. Okay. Now, one possibility here for voltmeter, let's say I want to measure the voltage here. Okay. Supposingly, let's say this is ground. For a simple one, what can be done is you can do something like this. Now, what is the voltage here? It will be the voltage here, right? Agree? Am I right? Correct? Now, what is your input here? Your R in will be infinity, right? Agree? So now you are free to add your voltmeter now. That will agree? So your voltmeter one end to the output of this, the other end to this side. You will be able to measure your V here. Second. Alright. So for the idea, okay, out of the 7 marks, this will give you 4 marks. After you mention the idea N, idea 4, whatever. So the other 3 marks. Understand? Well, I already mentioned to you, if you really want the answer I give it to you, right? In the last lecture, which is very complicated. If you want, you can only ideally, okay, which I mentioned in the last lecture, often I cannot have all the answers. Alright? Okay? But basically, now, that is what I mean by what is a UK exam. Okay? Now you notice in Asia exam, or at least in Singapore exam, your A is 80, right? Or 90. But UK is 70, right? It's quite easy. Okay, but the question is, if you look at all the questions, there is bound to have one question that is out of nowhere. Okay, so in case you see anything that's out of nowhere, just say the something, just do the rest of don't get too panic. Second, you don't agree with me, but that is the way the system is being created. If you look at the notes, it's very sketchy. Alright, in fact, I once told one of the students that the good thing about UK education, or for that matter, overseas education, is that the lecture notes are quite crap. The reason is this: the whole system is, excuse me, I'm quite serious now. The whole system about the overseas education is such that you want to inculcate you to be an independent learner. So basically, whatever that is given to you is like to give you the scope only. Is that clear? Because it's giving you a scope only, it's expected that if you really follow your student handbook, every 1 hour lecture you are supposed to read up another 10 hours by yourself, outside of the scope, but near to the environment, the carve-outs. Is that clear? So they have the liberty to come up with any question that they want. Is that clear? And in that being so, they will not expect you to know very 100% how. You understand now? Okay? And in the process of doing that, unknowingly you become what we call an independent learner, because you have to, based on what you are given, try to learn about it. Is that clear? Does that answer your question? Alright? So, as far as this is concerned, I will be able to give you about 4 marks. The other 3 marks, it is in the last lecture. Anybody got the photo? Remember, there's one day I bring in software with the op-amp and things like that one. Okay? Now that is the one, but in the exam, I don't expect you to be able to produce that. Second, there's no very. So for that, the 3 marks is more or less like taken away.
Coming up for examiner,
Alright?
Coming up for examiner.
Okay, any other questions on that? Now, again, op-amps it is kind of quite a popular question in the sense that if you want to emphasize a little more on the op-amp, there is quite a lot of op-amp possible questions. Like 1 year, there was this question on the, instead of output being a voltage, what is the advantage of output being your current? Okay, the note just now, you can follow the note. These questions on the noise one came out twice already. not quite often. Alright? And op amp, there's 1 year, in fact, I think 2 years also. Okay? So, these are also, so I mean, op amp, why is op amp very important? The answer is very simple. Op amp being one of the fundamental component that can be used to translate your input sense signal to either amplify it and to remove the noise. Agreed? So, ideally, you need to know a little bit of your characteristics of your op amp. Okay? How to configure it as an amplifier, as all kinds of things. Alright, so good thing to learn about if you wanted to. Okay. Alright, what's the next question? Sorry? Any other second question? Third question? Any question of Victoria? The difference between passive filter and active filter. Now, the passive filter, alright, passive filter, the filtering effect. Okay, first of all, passive filter, your gain. Passive filter, gain equal to 1 or less. Okay, active filter. Sorry, pass band gain. Pass band. This one pass band gain. More than 1. Okay. This one only LRC component. Okay. This one contains op amp or even transistor. Okay. These are what we call active components. Is that clear? Okay. So let's give ourselves a simple example of say a low pass filter. Example, a low pass filter will look something like this. A capacitor, V in, for example. Okay? And this is your V out. Okay? Now this one is a first order low pass filter. Okay? That's it. Okay? Now, how about first order active filter? The first order active filter will just look like this. Same thing. V in. Okay? And here, for example, that's it. Once you have a op amp, it is active. Second, that's all. Now, if I want to make this gain more than 1, can I? All that I need is something like this. notice that what is this one here? This is the what we call a non-inverting amplifier, for example. Okay, so this is also active. Active gain more than 1. Okay, now your gain here can be greater or more than 1. Passive filter, your gain, fast gain is always equal to 1. Active can be more than 1. More than or equal to 1. Okay? And what does it require? It requires an active component. Alright? And what are the active components? You could actually have a buffer, for example. Okay? And in fact, this happens to be one of the past questions where it talks about filter or multiple stages. And then how do you resolve it such that it's separate section by section? The answer is you can use your voltage follower. Second. Okay. What is the use of voltage follower? Isolation. From one stage to the other. Any questions? Alright, class, what he was trying to say is that, now, class, what he was trying to say is that active can be, let's say, pass band reset, and things like that. The truth is, active or passive, they all can be, all the four types of filters. Now, what are the four types of filters you could have? Class, you could have a low pass filter, which is something like this. Low frequency I want, high frequency I don't want. Alright? High pass filter, high frequency I want, low frequency I don't want. Okay? Then pass filter, somewhere I want. Too high, too low I don't want, too high I don't want. Is that clear? Now, how about band reject filter? Band reject filter, it is somewhere in between I don't want. Elsewhere, I do let it go. Now, why do you want to have, for example, band reject? Example, you see, you know where is our power line, right? Anybody know what is the power line you see? 50 Hertz, for example. Alright, US 60 Hertz. Now, what happens is, if you go to hospital, let's say you're monitoring your ECG. Okay, now what happens is your power supply is always bombarding your signal through your electrons. So in the end, what happens is you somehow pick up 50 Hertz. So imagine your signal is coupled with a noise of 50 Hertz. What happens? The noise is your signal is going to be very noisy. Okay, so if you want to design either a band reject filter at that 50 Hertz, remove the 50 Hertz component. Something like that. So that is the use of so-called band reject. Now, to answer your question, does it mean that only the active filter can be band pass or band reject? The answer is, if you look at this one here, class, excuse me, this one here, is this active filter or this is the tutorial 2, question 1. Okay, is this active filter or passive filter? It's a passive filter. Why? You only have an input. The rest are all discrete components. Okay, so at all time, what happens? Your gain is definitely less than 1. Is that clear? Okay? So this is actually a passive filter, but this one is a, what kind of filter? I forgot already. Now, plus, essentially, how does this thing work? When I have a capacitor and inductor, what to compare? Let's just draw this component first. Inductor, capacitor. Okay, let's recap. Capacitor, short circuit, and high freq. Agreed? Alright, this one I'm not going to repeat, otherwise I have no time. Inductor, short at low frequency. Agreed? Okay. At some frequency, at a certain okay. And when that happens, what happens? The take total will be is equal to 1 upon take L plus 1 upon take C, and the whole thing 1 upon it. It's going to be infinity. Agreed? So, in this case, let's look at here. In this case, low frequency, this guy wins, right? What will happen? You short this guy, right? Agreed? Low frequency, this is short circuit, so your output, what happens? Shorted. Agreed? High frequency, this one wins. You short the output also. So high frequency, low frequency, no output through this. Okay? Agreed? So, if let's say this is R now, look at R. Okay? Low frequency, inductor win. Inductor. High frequency, capacitor. Shorted, right? Agreed? Now, at somewhere in between, these two are infinity, right? Infinity is actually nothing there. Agreed? You can imagine that. Open circuit, no? So you can take out these two. So what do you see? All the signal will just go through R. Agreed? No? So at somewhere at the frequency of the impulse, so it becomes band pass. Is that clear? So this is a passive filter, but it is a band pass filter. Does that answer your question? Is that what your question? Sorry? Okay, so it is not true to say plus active filter, then you can have that. Now, the only thing about active filter is that active filter will give you gain more than 1. Second, and typically, active filter provides a better isolation. One state to the other. Second, yes. C and A stop. That's it. They are still in parallel. Yeah. You are trying to say how to do a band reject. Okay. To do a band reject, let's say these two C and L in parallel. To do a band reject, if you look at this, the only way to become band reject is this one become infinity, right? So one possibility is this. In fact, it's inside your lecture note. Okay? What you will do is your L, your C, okay? And now you connect to your load. This is your RL. Alright? And now here is my input. V in. So what happened? At low frequency, signal will go through, right? Okay? High frequency, signal will go through this part. Somewhere in between, this guy is open circuit. So you are going to see something like this. Low frequency signal go through because of inductor. Inductor is short circuit. Alright. High frequency signal go through because of capacitor. Somewhere in between, both cancel out. It becomes infinity. So almost signal. Remember this one? Somewhere in between, what happened? 1 upon 0, right? 1 upon 0 is infinity, right? Infinity means what? Whole circuit, right? So at the frequency of your interest, it becomes the whole circuit looks something like this. V in. RL. This one is infinity. So will any signal go through? Second. You are saying what? L and C or R and C? L and C. You swap, right? You are still in parallel. No different one. No difference. Because whether C is this side or that side, they are still in parallel. When they are in parallel, what is the total impedance will be the same thing, right? As long as they are equal and opposite, what will happen? They will cancel out, right? So it becomes 0, right? So 1 upon 0 will give you. Okay, what's the next question? Is it clear now? So, to answer our friends here, this active filter only can be used to implement band reject, band pass, or that kind of thing. The answer is 4 kinds of filter, low pass, high pass, band pass, band reject, all can be active and passive. In this case, what you see is the example of passive filter. Alright? Now, when we want to use active filter, plus some of your signal, for example, your bio signal, EEG, EMG, they are very big in terms of milliamp, microamp. So what do you need to do? You need to amplify them before you want to filter it. Second, so for such, typically active filters will be used. Does that make sense? You ask me. Alright, basically I'm saying this. When we want to use an active filter, you want to use active filter because you want to give the gain to the signal. Alright? And quite often, there are a lot of signals that when you capture, it is in milli or micro volts. It is very quick. So typically, you also want to amplify them along the way. Okay? So you may want to use the active filter. Is that clear? Alright, some of the signal, for example, if you look at the lecture notes, somebody has a lecture notes of chapter 3 or 4 where you see the power line when you do measurements.
What's your revision? Software in the instrument. Oh, so like a tuner.
First paper.
Now, plus, if you look at this system example, there's, you don't know which notes, I think chapter 9 probably. One of these system diagrams where it talks about, at some point, you notice that the signals are noisy as you transmit it, right? So what you need to do is, you just want to remove a high frequency noise. Okay? So what it does, is just use a inductor like this. Now what is the inductor class? Remember inductor is short circuit at low frequency, right? So at low frequency what happens? Signal go through. Right? Now inductor it is open circuit at high frequency, right? So what will happen to high frequency? It appears to be an open circuit for the high frequency component. Okay? So that will allow you to just remove the high frequency component. Is that clear? So that itself, by doing so, excuse me, this one itself is already a low pass filter. Is that clear? A very simple low pass filter, which is trying to remove the so-called EMC, electromagnetic conductivity. EMC. Right? So this is what we control. Is that clear? Okay. Does that answer? Who was asking? Yes, what I'm saying. So plus the filter itself can be very complicated or can be just as simple as that. Okay. Any other questions?
Answer.
Any other questions? Now, do your tutorial.
What?
If you
Going to in the market.
if you have no time to study, which I think you all have 1 month of Easter break. Okay. Any other questions? And lots of questions.
这你有换手机吗？没有吧？那我想，我说，Man City。一个人我拎，
赛了2个，
因为
2-6赛，
因为反正你
那个 OK 啊，
那个叫已经3-1了啦，2-1了，但是对。
3-1，doesn't matter。
现在天气也不是 last COVID，
Any other questions?
觉得。
There was one student who asked me about ball prop. Are you here now? Now, class, honestly, those people who email me making an appointment, you better show up. It's not so nice. This question of question 2, in the application of DC output, plus DC output sensor alongside with 50 Hz power cable, right? You reach, signal reach the instrumentation, become noisy. Draw the filter. Okay, so supposingly this is the measurement. You want to measure this. Now class, essentially, let's say, by the time you measure, it is noisy because along the way, your 50 Hertz will sort of corrupt the signal. Is that correct? So, what is the cure? The answer is this. So, signal of my interest is 0, right? Signal I don't want is 50, right? Okay? Now, what it basically means is in this scenario, signal of your interest DC. Correct? Signal you don't want 50 Hertz. I don't want. Agree? So what it basically means is I will make a filter of this kind. Okay? So I'm looking at a low pass filter. Right? And what is the low pass filter? Essentially it's just a resistor and the capacitor as such. And this is your V out. And here is your V in. Second. Yeah, it's up to you to whatever. You can be more stringent. If you want to be more stringent, by the time 50 is out of the band detect. Okay? So, you bring out a good point. Alright? Now, is 50 Hertz is the cutoff frequency or benchmark frequency? Okay? Now, and this is the difference between the so-called electronic people and the mechanical people. Right? I think some of you from electronics you know that. Strictly speaking, there's quite a lot of error in it. You agree, like, okay? But as far as the mechanical or those who are doing instrumentation, they just roughly want to remove certain things. So, but if you are more rigid about it, you want to know your spec of your filter. When you say you want to know your spec of filter, then, especially for the electronics people or instrumentation people, typically what they will ask is, what is my signal strength? And what is my noise strength? How much I need to remove my noise? How much I need to attenuate my noise? So that at the output, my signal to noise ratio is of a certain standard. Okay? And that itself will determine by that point, let's say 50 Hertz, how much attenuation you need. And that will decide whether it is going to be in a stop band or is it going to be a just the cutoff frequency. Okay? And so for that matter, since it is more or less set by the instrumentation mechanical people, you are just loosely speaking. Alright? So for that, it's fine if I put 50 here. If you are going to be more stringent, 50 should be cut off. So that will be totally new. After all, what is the signal of your interest? Your signal of interest is at DC, right? So why do you have to let it 50% of 50 Hertz come into your signal? You know what is up dB? 3 dB drop is the power drop by half. That means your attenuation is square root 2. Alright? V out over V in is equal to this. It's still quite a big component. Second, power is V out over V in square, right? Which is given you. Alright? 3 dB. Can you see that? Okay, 10 log 2. What do you get? Somebody calculator? Will give you 3 dB. Alright? Am I right? Oh, your class already. Dr. Chen will come down in 10:30, and then the rest of the time he'll take over. So we still have enough and now to ask questions. Okay, so agree somebody already work out already? 3 GB, right? Okay, so to answer our friend, class, when you want to be strict about your filter, strictly speaking, excuse me, if you are really doing an instrumentation, the real thing is that you need to know that what, especially for those doing live connector, you are looking at the weak signal versus your strong one. So for that, class, in order for you to achieve a certain signal to noise ratio and output, you typically have to ask yourself, at that unwanted noise frequency, how much attenuation I want it to be. Second, and that will decide what is the order of the filter and what is the cutoff frequency. Second, so in this case, our friend was asking, should the 50 Hz be at the cutoff frequency or at the soft end to be regarded as a method? Okay, that's the answer. Okay, but it's important that you need to know some of this, how to do these operations when, let's say, for example, capacitor cancel your inductor. And when that happens, what exactly happens to the practice that you propose? Alright? Okay? Any other questions? You have a question then? Okay, come. Okay, what are the questions in 2013? Yeah? 2013, I think this one is the so-called sub-paper. Now, class, IDS aim to pass for the first time. Sub-paper is harder. Serious. Now, this is what I mean by one of those things that you never see before. Alright? One of the questions asked is this. In DAC, supposedly linear, but sometimes you also have a so-called non-linear DAC. So the question is, what is the advantage? Okay. First of all, okay, what makes it more desirable means what is the advantage in that sense? Second, so the answer is this. Sometimes in your signal measurement, certain part of the signal, certain range of signal, there is more population. But certain part of the signal, less populated. For example, if let's say you look at a picture, some picture will have very low frequency content, but some will have a lot of changes. There's a lot of high frequency content, for example. Okay? So, supposedly, you want for alright, so in order for you to be able to differentiate a small change within a very populated, environment, it's good for you to make a resolution smaller. Agree? What I'm going to say. For example, let's say I have a scale. Okay? A lot of data occur in this range. Many data. Many data. Okay? And less data. And this one maybe less data. So if that being the case, in order for you to be able to sort of get a very good descriptions, you may want to have a better resolution at the point where there's many data, so that you don't introduce too many errors. Okay? So one possibility is that for this portion you want to have a better resolution, and here less. Okay? Or cost, C-O-A-S-T. Now, I'm sure you have not seen hear this before, right? This is the very first time you hear. Cost means rough scale. Have you seen this before? No, right? I cover in the supplementary and exam. Does it mean that it's upper? Okay? And in fact, there are others also. And this is what generally what it means by the UK standard. Or the overseas standard is like that one. They don't see one. But they can cover it. Because there's 30% they have. Alright? And I'm quite serious, so you don't expect anyone to know everything. No way. Because they can just cut off under the sun. Second, and remember this will be probably the 11th hour if you happen to read the article. Now you understand? So when I say I don't know, I'm not trying to say I don't do it myself. I'm just trying to tell you that knowledge is growing in many directions in the world. Okay? So there I follow the track of this information on this track. Okay? And the way the UK learning is trying to force you to be a learner by yourself. And if that happens, then anywhere you go, you will become. Is that good? Right? Do I answer your question? Whatever. Okay. So that is basically what it is. Alright. What is a linear and nonlinear? BAC? Well, essentially it's trying to do that. Is that good? Okay, so those populated one, maybe you want to have a better resolution. Those not so well populated one, after all your error is already occurring for each and every. Is that good? Then what else? Yeah. Okay, for this one here, one of the undesirable one will be you are going to have a lot of components. Alright? If it's referring to this one, the undesirable one will be you will need a lot of fresh comparator. DAC. Okay. One possibility is that your scale must be quite accurate. Otherwise, it will not be giving you the exact weightage. Remember for this one here, DAC here, DAC in order for you to accurately represent your input signal. In other words, okay, first of all, let's recap what is DAC. Okay, this question is basically saying that have the original question paper, often I cannot quite understand what it was. Anybody has this paper 2013 subpaper. The other one, the intrinsic, I don't quite understand what you want. Any other questions? So far, any question from Victoria?
Huh? Always go, University always go. Seriously, yeah. He only 2 times that we lose. 3-1. No, never play.
Right. This, okay. One of the undesirable DAC output that I can think of is, remember what is DAC? Digital to analog, right? So the digital to analog, typically your output will be stepped. Alright? Agree? Alright? Make sense? Steps, right? So it is a bit tricky. So one way to do it, but there's only one unrecovered effect. It's not smooth. So to do it is do a filtering. Okay. This is what I can think of. The other one could be, I don't think of it. So another 3 months, 4 months. Otherwise, it's not covered. So what else can I think of it? Right? But definitely DAC. Yeah. Right? Now, if you are talking about DAC, there's another issue you need to ensure. Plus, ADC and DAC typically are operating on the clock, right? Okay? Now, plus, ADC, DAC typically are operating on the clock. Sometimes, some of these devices, the clocks are actually jitter. If you go and do a Google, look up the word jittering. You have a handphone, right? You can find out this word, jittering. Jittering. J-I-T-T-E-R-I-N-G. Now, essentially, what is this error? If your clocking system is actually, your clock frequency change over the time, that is called jittering. It will actually introduce your signal error as well. Signal. So, to remove that, you will probably need to ensure quite a stable clocking system. Alright? So these are some of the things. The other thing about DAC is, because it's discrete, correct? So your signal will. What I'm trying to say is something like this. Let's say, for example, if analog, the signal is smooth, right? What is the digital one? The DAC, your ADC or something like that, right? Okay? Correct? And remember your DAC, your DAC, it is a binary to analog, right? So what it means is you also have a discrete steps, right? Agree or not? Okay? So one possible error, if you ask me, your output will be in steps, right? So how do you want to smooth it? You can use a filter. Alright, so one way is using filter. Secondly, what you can do, better resolution. Okay? That means from one step to another step. From one step to another step, it's closer. Okay? That will reduce the error. Otherwise, like for example, let's say 4.5. See, it's the same idea about DAC and ADC. If my number of bits are better, hopefully the difference between one signal to another signal, the difference will be smaller. Otherwise, you can get truncated out. Is that clear? Alright. Better revision. Reduce the truncation. Error. Is that clear? So these are some of the things that some of the possible errors that will be introduced in the process of digitizing. Is that clear? ADC, let's say for example, I have many signals, but I only have 8 bits. What will happen? From one signal to another signal, you get chopped off quite a lot of information, right? If I were to make it to 12 bits, my resolution is better, right? You understand what I mean? So the same thing. For DAC, if I have 12 bits, that means my representation of my signal will be smoother, right? If I have 10 bits, it will become more blocky. So this is one truncation error. Okay? The other one will be, the blockiness, then, so these are the errors that you have. So in order for you to reduce it, you can use a filter, you can use a better bits that you have. Alright? Okay? Okay. Anything else? Send this to me as well. I don't have access to the database for the. I only have the journal access to the journal. So I have limited access to the IDO. Students are better lah. It's like that. What else? Are you given the financial area? Okay, do you need to go in depth for the physical electronics or whatever? Now, plus, these are questions unfair in me. Okay? Now, essentially, in the learning, class, in the learning, for every chapter, you ask yourself what is the main principle behind it. At least know how operating principle, just in case they ask. Okay? And then, Any other questions? No, you don't have to wait until the question you answer. You can always come down and tell your Any other questions coming down? BAC whether you connect to which side of that, okay, the one don't have to. But this one is a generic question. Okay. Now close. Once here also there's one question about, are you the one who asked the more problem? Who is the one? Okay, plus. Typically, sometimes in the past years, they also prevent you, excuse me, can I have your attention please? So this is a very, the question that I would expect a lot of people know how to do it, but to my horror, a lot of people don't know how to do it. Alright. So, now class, the presented scenario is this class. If I have any signal, I would say that all of these are the so-called Fourier spectrum. Now what is the Fourier spectrum? It basically tells you where is the occurrence of either signal or noise. Is that clear? Now, what is signal, what is noise? The answer is we don't know. Signal is basically the one that you want. Noise is the one that you don't want. Is that clear? So, let's say if I want, okay, in this case 0, 100, 10,000, and then this one is 100,000. Okay, supposing the only thing that I don't want is 100 Hertz, then what is this? What is the noise? 100 Hertz. The rest is signal. Is that clear? Alright. So, and let's say supposedly the only thing that I don't want is the 0 Hertz. Then 0 Hertz is the noise. Is that clear? Okay, so even a spectrum like this, whether you use a band pass filter, band stop filter, high pass filter, or any filter, depends on the question being asked. Is that clear? Okay, so at this moment, nobody knows yet. Until the question is described. For example, in this case, the question says something like this. The component of 10,000 Hertz is unwanted. Alright. It's only this one here, and we would like to remove it. Class, only this one no. So, in this case, it is this one here I want, I don't want. This one, I don't want. Is that clear? So this all others I want. Okay. Strictly speaking, you will want to design a filter such that something like this happens. So that this guy will be removed. Is that clear? Okay? So supposing the same one plus 0 here, 100, then 10. Okay, and then 100K. Supposing that I tell you this is not what I want, then what do I do? I don't use very fast. I use the low pass. Is that clear? Okay, so spectrum is still the same, right? You understand now? So filter, I'm so amazed that here, almost everybody got it wrong. Only a very 20% got it right. Okay, now they don't actually expect you to know exactly where the cutoff frequency, but at least you need to get the band stop in this case. Because why? That signal happens to be between all others as well. You have to band stop it. Second, supposedly class, the same thing. Same thing again. Here, then K. 100K. And I tell you, 10K is the only thing I want. If 10K is the only thing I want, then how? I only want 10K to become something like this. Only 10K. This one is 100K, I don't want. Don't want. This one is 10K. Don't want. So you have to ask yourself, what future profile will fit your needs? The second is not just by generalize. Happened that the year before was a low-pass filter. Everybody had some low-pass filter. And that's precisely what you do. You laugh at them. Alright. Is that clear, class? Any other questions? Question? This paper, question one. This question is this one is already out of syllabus. And then they talk about the material use. But since they already devised it, so not necessary. Okay? If you look at the question carefully, it talks about the kind of material to use. Now, if you look at this one here, it talks about consideration. As far as the new revised syllabus is concerned, it basically apart from the working principle of the thermocoupler. Right, so not so much of that. Okay, but essentially, off the cuff, this is what I remember. That the way the thermocoupler works is you have material 1, material 2. Put together. Alright? Tie together, and there should be what else? This one here, it only measures the temperature gradient. Okay, not. Okay, this is only thing that I remember. That's why I